you for reaching out for me about that quiz thing. I hadn't noticed it, so thanks for letting me know. Appreciate it. Let's see. All right, y'all. So let's see. Weekly activities folder. Hello, Jennifer. Come on in. Come on in. Let's see. Did I hear a little something here? Yeah, I heard a little something. All right, good. Thanks, Noel, again. Let's see. All right, y'all. So week 10. Let me edit this part right here because it should say also 4.8. They're in there. So again, that number. Okay. So what we're going to do today, y'all. Let's see. I have the notes for 4.6, 4.7, and 4.8 here. So let's see. Today, what we're going to do, we're going to do 4.6. We're going to just do two problems out of 4.7. I think in the notes, I have a total of 5 questions out of 4.7. We're just going to do 2 of them today, and then we'll finish up 4.7 and 4.8 on Wednesday. So we are going to do 3 sections again this week, y'all. I have a little calendar. I don't know if I don't keep it with me, but it's at home on my desk. And I think after this week, we'll be able to go back just to doing like 1 section a day. But again, I want to make sure that we do have time to get stuff done, and I don't want to be rushing. And I think we can manage the stuff that we got right here. So, oh, John, I did send you back a message whenever you get a chance. You don't got to do it right now. But so y'all, the notes for 4.6 are right here. So again, you can always access them. And y'all, I'm trying to make sure that I can set up this stuff for you guys. Like, so I think I had messaged you guys maybe Friday saying, hey, this stuff is there. So in case you want to print them out or access them somehow, you'll definitely have the notes before you come to class, okay? So what I did, y'all, is I have the notes here in my OneNote. So let me just come back up a little bit. Let's see, we already did that, so we don't got to look at that right now. We did this, obviously. And here we go. Huh? Oh, don't worry, John. When I was doing the problem myself, I was doing exactly the same way you did, and then I realized, oh, that was the boo-boo that we both made. You know what I mean? We have to set it equal to that. You're talking about the homework problem?
Yeah.
Yeah.
I didn't know. Like, I was looking at it, I'm like, what am I doing wrong?
Yeah. It's all right. Don't worry. We got it. All right. So, y'all, 4.6 talks about limits at infinity and asymptotes. And so, when those of us who had pre-cal and we looked at the graphs of the different trig functions, a lot of the trig functions, or at least some of the trig functions, had vertical asymptotes. Like secant, cosecant had them, tangent and cotangent had vertical asymptotes. And so, y'all, I'm actually going to see if I can pull this up real quick because I want to say I'm pretty certain that here in our Blackboard page, let me see. Here we go, like formula sheets, chapter notes, all that kind of fun stuff. I want to say that maybe, oh man, I don't know if it's here. If it's not, I mean, I'll pull it up in a little bit, but no, it's not on this one. I was just curious to see if I had given you guys something like that. I think this is just a table, right? Yeah, this is a table. But I'll tell you what I'll do, just to kind of give you a heads up. Let's see, let's go to Drive here. Let me go to my pre-cal. And there we go. So, y'all, this is, and again, I'm just going to kind of show you, but like this is the cosecant graph, right? And so the cosecant graph has these vertical asymptotes, right? So that's what the vertical asymptotes look like. Again, if you remember any of this stuff from trig or pre-cal, whenever it is you might have had it, even though it was in high school. But these are what we call vertical asymptotes, right? The idea is the graph gets really close to them, it doesn't touch them, or as I approach those x values, the y values either go up like they're going towards positive infinity, or they're coming down like they're going towards negative infinity, things of that nature, right? So what we're actually going to do here, we're going to talk a little bit about limits towards infinity, which is going to deal with something called horizontal asymptotes. And we're going to talk a little bit about vertical asymptotes as well. So first off here, we have something about limits at infinity and horizontal asymptotes. Okay, so what I have here, y'all, this is just a rational function. We talked a little bit about this in college algebra. Again, if it's been a little while, don't worry about it. I'm going to kind of walk you through it. But this is what graphs of rational functions look like. Rational functions, in essence, y'all, mean that um, we have a fraction in our function, and the fraction has a denominator where the variable appears. So if you notice here, there's my fraction. Look at the denominator. The variable appears in the denominator. Okay. So when we're talking about limits towards infinity, what we're thinking about is I'm going over here on the x-axis, right? So here's my x-axis. You can kind of see it here. As we continue to go to the right, we go towards larger numbers, like we're approaching infinity. As we go to the left, we're approaching larger numbers, but in the negative direction, going towards negative infinity, right? And so horizontal asymptotes are these horizontal lines that as the graph goes either towards infinity or towards negative infinity, the y values get closer and closer to that value. So I want you to look at the y value that we have here. It's y equals 2, okay? I want you to think about the function that they gave me here. So the function they gave me was f of x is equal to 2 plus 1 over x, right? That's the function that's been defined. I want you to think about if we were to start plugging in values that were getting really, really, really big, okay? So look, let's do something like this. We're going to find a couple of function values. We're going to find f of 10, we're going to find f of 100, and we're going to find f of 1,000. So first thing we're going to do, we're going to come back to this function here, and everywhere we have an x, we're going to plug in a 10, right? So let me grab my calculator. Here it is. And let me turn this guy on. Let me clear it out. Let me go to my y equals. And I'm going to put 2 plus, and I'm just going to do this in parentheses, y'all, 1 divided by x. Okay. And I'm going to enter that in. Okay, let me quit this. We're going to evaluate our function at the first time we set at 10, right? So I want you to think about it. If I plug in the number 10 right there, what's 1 divided by 10? 1/10, right? 2.1. That's right. So look, when we plug that in, look, 2.1. We're going to do the same thing at 100. So back over here, we're going to do this at 100. Everybody agree 2.01? Because it's 1 over 100, right? So 2.01, what do you think is going to happen at 1,000? That's right, 2.001. So y'all, as this number gets really big, do you agree with me that this number here gets closer and closer to 0? Because 1/10 is 0.1, right? 1 over 100 is 0.01. 1 over 1,000 is 0.001. So as x gets really big, when x is in the denominator, the entire fraction is getting closer and closer to 0, right? Now, y'all, we could play the same game over here, and we could say, look, let's find f of negative 10, f of negative 100, and f of negative 1,000. And if you remember at the beginning of the semester, we did something very similar to this. Okay, so let's change this now to a negative 10 and 1.9. And if we do this again, but now at a negative 100, 1.99, what do you think is going to happen at 1,000 or negative? 1.999, right? So as my numbers, y'all, as they're getting either really big in the positive direction or they're getting really big in the negative direction, look at what the y value is getting closer and closer to. The y value is getting closer and closer to the number 2, right? That's what we call horizontal asymptotes, all right? So let's see, and it tells me right here, the function approaches the asymptote y equals 2 as x approaches both positive and negative infinity. So again, as I go further and out to the right or further out to the left, our graph here, those y values get closer and closer to 2, and those y values get closer and closer to 2, right? Okay, so we have an informal definition. It says the values of f of x become arbitrarily close to L as x becomes sufficiently large. We say the function has a limit at infinity and write the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity is equal to f of x, is equal to L, right? So in this case, the L number would have been the 2 because we were getting closer and closer to 2 as we went to either positive or negative infinity. Yeah, we've talked a little bit about it before. It's just kind of review-ish. Okay, so what we're going to do here, y'all, we're going to do a little stare and compare. We're going to look at our graph, and we're going to do it in pieces, okay? So let's do this. Look at part A. It says, what's the limit as x approaches infinity of g of x? So this is our graph, y'all, of g of x. As x goes towards infinity, so as we're going this way, right? What is the y value getting closer and closer to? So as I move further out this way, if I were to go up, what y value would I hit? 5, right? Because as we're going to the right, as we continue going to the right, the y values are getting closer and closer to 5, right? Okay. Now, we're going to do part B. Look at part B. It says, what's the limit as x approaches negative infinity? So now my x values are moving this way, y'all. As I'm moving this way, what are my y values getting closer and closer to? Negative 5. Okay. Okay, question. Does anybody remember what this means here? When we have the limit as x goes to negative 4, but then there's kind of like a little exponent of a negative sign. Do you remember what that meant? It's approaching from the left. Excellent, y'all. So look, we're coming in this way. We're getting closer and closer to the number, oops, negative 4, sorry. We're getting closer and closer to the number negative 4. What are my y values going towards? If they're going all the way down here, what would we say? What would our y values be going towards? Negative infinity, right? Okay. All right. Now, what does this one mean? As x is approaching negative infinity with that little plus, what does that mean? Anybody remember what that one means? That's coming in from the right. Good. So look, I'm coming in this way. Aren't my y values still going further and further down towards negative infinity? Okay. Now, question, y'all. Look at part E. Would you say the limit exists now? Yeah, it does, right? If the limit from the left side and the limit from the right side are the same, then that's going to be the limit as x approaches negative 4, right? So remember, I know it's been a little while since we talked about this. Like, okay, if we're trying to find the limit as x approaches a particular value, we're first going to look at what happens as I'm coming in from the left, what happens as I'm coming in from the right, and as long as those values are the same, that's going to be my overall limit, right? Okay, so look, let's do the same thing for part F. So look, we're now looking at the limit as x approaches 5 from the left. So I'm going to scroll up here. Let me clean up some of this mess. And I'm coming in from 5 to the left. As I'm coming in this way, what's happening to my y values? They're getting what? Bigger and bigger and bigger. So wouldn't those be going towards infinity? Okay. Now we're going to take the limit as 5 as we approach 5 from the right side. Okay. So look, let's approach 5 from the right side. I'm coming in this way. Look at my y values. Are they getting bigger? Yeah, so we're still approaching infinity, and then that's going to be my limit overall. Right? Good, very good. All right. So you know what? I think I am, but I'm going to double check. I'll make sure I'm recording. Yes, we is. Okay, we're good. All right. So let's see. Okay, so now, y'all, we're gonna figure out how do we find the limit when we have actual functions here, when we actually have a function that's been defined and we have the expressions defining those functions. So if you look here, the first one is we're taking the limit as x approaches infinity of 1 plus 7x over 5 minus 8x. Okay, I want you to think about this for a little bit. If my x numbers were getting bigger and bigger and bigger and bigger, what would happen to 1 plus 7x? Would that continue to grow? So think about it this way, x is getting bigger and bigger. So we're taking numbers like 10 or 100. Right. So if we plugged in 10, it would be 70, right? 71. If we were to plug in 100, it would be 701. If we were to plug in 1,000, it'd be 7,001, right? And then if we were to plug in those same numbers down here, like say we were to plug in 10, that would be a negative 80. 5 minus 80, negative 75, right? So what's happening? These numbers are getting really big in the positive direction, and these numbers are getting really big, but in the negative direction, right? And it's hard for me to figure out, okay, what is that value going to be? So when we can't just like plug in the numbers and say, because we can't really plug in infinity, right? But when we can't do this, what we're going to do, y'all, is just a little bit of algebraic manipulation. I'm going to show you something. I'm going to factor the letter x out of that first expression. And I know everything we've been taught up to this point says, hey, we can't factor out an x because there's only a 1 in the first part. We can actually do it like this, y'all. And let me ask you a question. If I were to factor out that x and distribute the x back, would I end up with what we have right here? So look, if I were to take an x times this, wouldn't that be an x over x? And if I were to take an x times that, wouldn't that be a 7x? And isn't x divided by x the same thing as 1 plus 7x? Everyone agree? Okay. So look, what we're going to do, we're going to factor out an x out of this first expression. Okay. Now, we're going to do the same thing on the bottom, y'all. We're going to factor out an x out of the bottom. Okay. If I factor an x out of the bottom, let me ask you a question. What am I going to end up with? Just like the same way we did right here, how could I write an expression in here so that when I multiply that x, I end up 5 over x minus 8. Everyone agree? Okay. Before I take my limit, y'all, we can do some canceling. Let's drop this x and that x because we can reduce those. Now we're going to take the limit as x approaches infinity of 1 over x plus 7 and 5 over x minus 8. Okay. Now remember what we said what we're doing. We're taking the limit as x approaches infinity. So we're thinking about x is getting bigger and bigger and bigger. If x continues to grow, what would 1 over x look like? It would be really, really small, like 1 over 10, remember? 1 over 100, 1 over 1,000, so like 0.10, 0.01, 0.001. So as x goes to infinity, y'all, this here approaches 0. So look, I'm going to write 0 plus 7. As x gets really, really large, would you agree that 5 over x also gets really, really small? Because think about it this way, 5 divided by 10, 1/2. 5 divided by 100, 1/20. 5 divided by 1,000, 1 over 200, right? It gets really, really, really small. It's a little bit slower, but again, as we take really, so even if we didn't take, say, 1,000, suppose we took 1,000,000,000, it's still going to be really, really, really small, right? So this number approaches 0 and over a 0 to minus 8. So what's 0 plus 7? 7. And 0 minus 8 is a negative 8. And that's what we approach. Okay? So again, if I think about that for a second, y'all, as I think about as my X numbers get really, really, really big. And again, I just want to kind of illustrate that here for y'all. So look what we had. We had 5 divided by X. So suppose we took 5 divided by, what's that, 1,000, 10,000, 100,000, a million, right? 5 times 10 to the negative 6. If I subtract 8 from that, this number should be really close to negative 8. Look at that number, negative 7.995, right? Now, I took a million. We could have taken a billion. We could have taken a trillion. And look, I mean, we are almost right there at negative 8, right? Same thing over here. 1 divided by a million. 1, 2, 3, 4, 5, 6. And then we add 7 to it. This number should be really, really close to 7. Okay? So we're gonna, with these problems here, y'all, we're gonna play some of these games, and then I'm gonna give you all some like general guidelines on how you can figure out what these limits are gonna be useful to you. Okay? Let's do the same thing here. What I would like for us to do, y'all, in this problem is let's look at the denominator first. Okay? That's a polynomial, right? So they're both polynomials. This is a polynomial of degree 2. What we're going to do, y'all, is we're going to factor out the x squared, okay? If we factor out an x squared, can anybody tell me what would we be left with? So if I took 11 plus 4 over x squared, right? Good. And y'all, again, if we were to distribute this x squared back to each of these terms, we would end up with exactly what we have right there. Okay, just like we factored an x squared out of the bottom, we're going to factor an x squared out of the top. Whatever we factor out of one, we're going to factor out of the other. And we're always going to look for the biggest term we can factor, okay? So out of the bottom here, since the biggest term I could factor was an x squared, I want to factor an x squared out of this piece too. So the question I want to ask you now is, if I did factor out an x squared, what would we be left with? 8 over x, very good, plus, very good. Before I go on, are we okay in how we got to that part? Jennifer, am I doing okay here? So again, I want you to think about this. If I were to multiply this one here times this guy, wouldn't I end up with an 8x squared over an x, which is really just an 8x, which is what I have right there, right? Because we're crossing out one of this x here with one of those right there, right? And then wouldn't both those x squareds cancel with both those? So I would just end up with the 11. Is that better? Okay, just want to make sure that we're all good here, y'all. Okay, just like we did before, we're going to go ahead and cancel out these x squared. So look what we have now. We have 8 over x plus 11 over x squared and 11 minus 5 over x plus 4 over x squared, and we're still taking that limit as x approaches infinity. Okay, so remember what we said, x is getting really, really, really large. If x is getting really, really large, wouldn't both of these here convert or approach what number? 0, right? Okay, so on the top, we're going to have a 0 plus a 0. On the bottom, wouldn't these also approach 0? Because that x is on the denominator, and if x is in the denominator and x is getting really large, that fraction gets really, really close to 0. So I'm going to have 11 minus 0 plus 0. So wouldn't this just be 0 divided by 11, which is how much? 0. Okay. Okay. So look, y'all, we're going to do this next one here. You okay, John? Oh, I hope you need to go walk a little bit. Okay. By the way, those of you guys are home, John is not getting sad. He just feels that way, right? Nobody's hurting. I just want to make sure everybody at home is not freaking out. Okay, y'all, we're gonna do the same thing here. We're gonna look at what is the largest term that we can factor out of the top, and what's the largest term we can factor to the bottom, and then which is the largest term overall. So out of the upstairs, what do we factor out? That's what we're gonna factor out of everything. Okay? So if we take out an x, that's right,
No matter the top or bottom?
no matter top or bottom. Good question. Okay, y'all, if we factor out an x squared, what are we left with upstairs? Excellent. Okay. If we factor out an x squared out of the bottom, what are we left with? Perfect. Okay. All right. Just like we did before, y'all, we're going to drop those x squared. We're going to cancel them out. And now we're going to say, look, we're going to take the limit as x approaches infinity of 11 minus 9 over x plus 8 over x squared over 3 over x plus 9 over x squared. Okay. All right. Everybody agree that the terms that I'm circling now are going to approach what number as x gets really, really large? 0. So we're going to have 11 over, or 11 minus 0, I should say. Look at it, but I'm going to keep the right sign. Plus 0 over 0 plus 0. So this is 11. Now remember, these numbers here are getting closer and closer to 0. Okay. Now, does everybody agree we cannot divide by 0? We can't divide by 0, right? Remember, these numbers are getting closer to 0. So they're not exactly equal to 0, but they're really, really close. If this number on the numerator stays gets closer and closer to 11, and this number on the bottom gets smaller and smaller and smaller, but these numbers here, y'all, are going to be positive, right? Because x is getting bigger. So it's 3 divided by, like, say, a million, plus 9 divided by whatever a million squared is, right? These numbers are still going to be positive. So I want you to think about this for a second. If we were to take 11 divided by, oh, I don't know, I'm just going to do something like this. Or not, I'm sorry, yeah. 11 divided by 0.00000. Right, we said the bottom number is getting. Do you think my answer is going to be a big number or a small number? Huge, right? 1.1 times 10 to the 14th, right? So that's 1.1 times 10 to the 14th. 10 to the 14th means 10, or 1 with 14 zeros at the end, right? So this number is getting really, really large, y'all. This value here is approaching what? Infinity. Okay. Now, I'm going to give you guys a little rundown so that we can do a shortcut in a second. You don't have to go through this process every single time.
How did you make it so you're saying 0 is equal to like a number of instances of 0?
Yes, because remember, x is getting really, really big. So as x is getting really, really big, this is 3 divided by a very large number and 9 divided by that large number being squared. So isn't this number here getting smaller and smaller and smaller? But it's still going to be positive though, isn't it? Because x is getting bigger and bigger and bigger. So I was saying, well, like what in essence is 11? Because the top number is also, those numbers are approaching 0. So roughly I'm going to have an 11 on the top. And if I have an 11 on the top, but I have a really small number on the bottom, what happens? My answer gets infinitely large, doesn't it? It approaches infinity. Okay, so y'all, I'm going to show you now a little rule so that we don't have to do this process every single time. Okay? I want us to come back to the first problem that we did right here. Okay? I want you to look at the first example that we did. What is the power of the x on the top? What's this? 1. What's the power of the x on the bottom? 1. Okay, so we're going to make a little list of rules here. We're going to say, how do we find our horizontal asymptotes? Come on, Richard. Okay, how do we find our, there we go. How do we find our horizontal asymptotes? Number 1, if the degree of the top is equal to the degree of the bottom. What I mean by the degree, the highest power of the x. Okay, that's what we call the degree of the polynomial. What's the highest power we have? Since they were the same, look at the answer that we ended up with. Didn't we end up with a negative 7 over 8 or a 7 over negative 8? What we're going to do, y'all, we're going to take the fraction of the leading coefficients of those terms. Okay? So over here, I'm going to write my horizontal asymptote is y is equal to a over b, where those are the leading coefficients. No, top. It's supposed to be a t. Sorry about that, y'all. The degree of the top is the same as the degree of the bottom. Does that make sense? Okay. If the degree of the top is the same as the degree of the bottom. Now, we're going to go to step number 2. So we're going to come back over here and we're going to look at the second one that we did. Here's the second one we did. Okay. What was the degree of the top? 1. What's the degree of the bottom? Okay. So, here we go. If the degree of the top is smaller than the degree of the bottom, the horizontal asymptote is going to be y equals 0. Look at the horizontal asymptote we ended up with. As x got really, really large, our limit ended up approaching 0. Okay? As long as the degree of the top is smaller than the degree of the bottom. It doesn't matter how much smaller, y'all, as long as it's smaller. Okay? So the degree of the top was 1, the degree of the bottom was 2. The bottom one could have been a 12. It wouldn't have made a difference, as long as the top one is smaller than the bottom. Case number 3. What was the degree of the top in this one? 2. What was the degree of the bottom here? 1. Okay. So case number 3. If the degree of the top is bigger than the degree of the bottom, the limit as x approaches infinity, well, it could be either infinity or it could be negative infinity. And we'll have to go through different kind of case scenarios. But in this case, y'all, there is no horizontal asymptote. Okay? There's no horizontal asymptote. Horizontal asymptote, y'all, is always going to be a horizontal line. And so if we're getting really, really, really big, we're not getting a horizontal line. Okay? But there won't be a horizontal asymptote. But the limit will either be positive or negative infinity. We'll kind of have to figure it out as we go through it. Okay? All right. So this part right here, y'all, I think is like super helpful, because instead of me having to like do all that factoring every single time, I can kind of just look at this and then figure it out from there. Okay. We're going to talk about that right now. Okay, because you're talking about this problem, right? Okay. So look, y'all, what is the degree of the top? 30. This is what we call the leading term. What is the degree of the bottom? 3. This is what we call the leading term. Okay? The leading term is always the one that has the highest exponent. Okay? So in this case, they both have the same degree. So as the limit approaches infinity, y'all, my answer is going to approach y equals, I'm going to take the fraction of the leading coefficients, 9 divided by negative 3, which in this case would be negative 3. Does that make sense? That's the horizontal asymptote. That's right. And that's what happens as the limit approaches infinity, the y value approaches negative 3. Okay? All right. Let's do the same thing for, okay, now we have something a little bit different. Okay? Now we're dealing with exponential functions. Okay, so let's take a look at what's going on here. Let's do part A. We're going to take the limit as x approaches infinity of 2 over e to the x plus 6. Okay, so 2 over e to the x plus 6. We're looking at the limit as x approaches infinity. Okay, I want to ask you a question. If x is getting really, really, really large, what is happening to e to the x? So it's becoming a huge number, right? Also, look, I can turn on my calculator. Remember where e to the x is? It's right above my ln, right? So if I were to say, look, what's e to the power, I don't know, 1,000? Overflow, it's too much, right? Apparently my calculator can't even do that. So, yeah, my calculator wouldn't do it, right? Look, I hit enter, there's overflow. Okay, I go to, I'll tell you what. Look, there's e to the 100. So look at what e to the 100 is. 2.68 e to the 43. Remember what that means? 2.68 times 10 to the 43rd power. That is a 1 with 43 zeros after it. That number is massive, right?
That number is probably like, so big, there's probably like less brains of Sam or
Something like that, right? It's so big. Okay, so look, if x is getting really big, this number is obviously getting massive. Adding 6 to it isn't really doing that much to it, right? Because it's like, here's, like a long time ago, there was a joke, and it was about, I don't know if you remember who Johnny Carson was, but Johnny Carson used to be a talk show host at night. He was kind of like Jay Leno, those kind of guys, right? And he's married and he's making like, I don't know, $300 million. And he gets, he hooks up with some girl, he marries her, and she's like, okay, now I make, $100 a week. So now we get 30 million plus $100 every week. You know what I mean? Like it doesn't really change that much, right? Okay, so as x is getting really large, this number itself, y'all, is getting bigger and bigger and bigger. So 2 divided by a massive number, what would we approach? No. Say it again, Steve. We would approach 0, right? Because 2 divided by a number that's so big would give us a number closer to 0. So this limit here, y'all, approaches 0. So look, I want to put this over here, y'all, just as a side note, okay? If I have a fraction, okay, and I'm taking the limit as x approaches infinity, if the denominator gets really large and the numerator approaches, I'm going to make this up, a constant, so I'm going to call it k, over a large number, this whole thing approaches 0, okay? Because if I have some constant divided by a massively large number, that number is going to get closer and closer to 0. Okay, now let's do part B. Part B says, look at the limit we're taking now, y'all. We're not looking at the limit as x approaches infinity. We're looking at the limit as x approaches negative infinity of 2 e to the x plus 6. So yeah, think about what that would look like. Let me grab my calculator. So look, I'm going to go second ln e to the, say, negative 100, right? And I'm going to hit equals. Is this number getting really, really big, or is this number getting really, really small? That number itself is approaching 0, isn't it? Yeah, so this number here, y'all, if we take the limit as x approaches infinity, this number here is approaching 0, isn't it? So if this begins to approach 0, that would approach 2/6, and 2/6 is the same thing as what?
1/3.
1/3. Good, very good. Okay, so let's take a look here at the next one, y'all. It says a function is said to have a horizontal asymptote if either the limit at infinity exists or the limit at negative infinity exists. Show that each of the functions has a horizontal asymptote by calculating the given limit. Okay, so first thing is, when I read the directions, y'all, I want you to notice this part right here. It says, show that each of the following functions has a horizontal asymptote by calculating the given limit, right? Okay, so if we're going to do this, that's telling me that I should end up with an answer in every one of these problems because it's telling me that I'm going to have that horizontal asymptote. Okay, let's see. I think we can do the first one probably together. Let's do it. Let's see if we can't figure this out. Remember what we said. What's the degree of the top? 1. What's the degree of the bottom? 1. We're going to take the fraction of the leading coefficient. What's negative 8 divided by 2? Boom. That one should be easy enough for us to do, right? Y'all, I'm going to skip over to this one. The only reason I'm going to hold off on this one just right now is because now we're talking about a limit as x is approaching negative infinity. We'll come back and revisit that in a little bit. But could I do this one here the same way we did the one we just did, right? The degree here is 2. The degree here is 2. What's the number in front of this x squared? 1. So we're going to take the fraction of the leading coefficient, and everybody agreed that's going to be a negative 1/2? Okay, good. All right, now let's do the same thing over here. We're going to take the limit as x approaches negative infinity of x to the third plus 15x minus 14. Okay, so look, y'all, let's do this. Let's use the same approach that we were doing at the beginning of the class. Out of the denominator, do y'all agree we could factor out an x to the third? Okay, and if we factored out an x to the third on the denominator, on the bottom part, what would we be left with? I'll give you a hint. 1, right? That'd be the first part. What would be the second term? 15 over x2 and minus 14 over x3. And out of the upstairs, y'all, if we still factored out an x to the third, wouldn't we end up with a 9 over x squared minus an 8 over an x to the third? What do you think? Does that look right? Okay. So now, look, let's go ahead and get rid of these x to the third. We're still taking the limit as x approaches negative infinity of 9 over x squared minus 8 over x to the third, 1 plus 15 over x squared, over x squared minus 14 over x to the third. Okay, now remember what's happening with x, y'all. It's becoming very large, but in the negative direction, okay? So I want you to think about this for a second. Negative 14 divided by a massively large negative number. What would that approach? That would still approach 0, wouldn't it? That would still approach 0. Okay, 15. Remember, x is going towards negative infinity, but if I'm squaring it, it's going to be positive, right? So I took, like, say, negative 100, but I squared. Negative 100 squared becomes a positive, like 10,000. So wouldn't this piece also approach 0? Okay. What would happen to this one then? What would happen to that 9 over x squared? 0. And what would happen to the negative 8 over x to the third? 0. So what are we going to end up with on the top? 0. On the bottom, we're going to end up with a 1. What's 0 divided by 1? Still 0. Okay. Look, y'all. We could have done it. We could have still looked at the exponents, right? I wanted to go through this one here, John, because I wasn't taking the limit as x approaches infinity. We were actually taking the limit as x approaches what? Negative infinity. So I wanted us to. We're going to go through the confirmation, make sure we can still do that. Okay. So the next two that I have here, y'all, we're taking the limit as x approaches infinity of the square root of x squared plus 4x over 11 minus 11x. Okay, so let's think about this for a second. That the big square root does mean a power 1/2. I'm going to ask you all a question. Inside my square root, if I were to factor out an x squared inside the square root, what would we be and what would we end up with? Before I go on, everyone agree with John? 1 plus 4 over x? Okay. Let's see. I'm going to leave the denominator exactly as it is right now. We'll do some fancy manipulating in a little bit. Second thing, y'all, since we're taking the square root, does anybody know what's the square root of x squared? Okay, the square root, I'm gonna do this on the side, y'all. I want you to think about this for a little bit. The square root of x squared, it's actually what we call a piecewise function. In college algebra, or at least when I teach college algebra, guys, we talk about piecewise functions. We talk about them extremely briefly. Okay, but I'm just going to kind of tell you what x squared looks like. The square root of x is equal to, or the square root of x squared is equal to x when x is bigger than or equal to 0. It's actually equal to negative x if x is a negative number. I want you to think about what this means for a second. Suppose I'm asking you, what's the square root of 5 squared? Well, the square root of 5 squared, is this number positive? Yeah. Then it's just equal to that number, okay? But if I were to do this, it wouldn't be equal to the negative square root of 5. It would be equal to the negative of negative 5, which is positive 5, okay? So if the number here is positive, it's just the number itself. If the number here is negative, we're going to put a negative in front of it so that the negative and the negative make it into a positive number, okay? So look, let's scroll back over here. Because we're taking the limit as x approaches infinity, what kind of numbers are we looking at? Positive numbers. So it's going to be equal to x over 1 plus 4 over x. Yo, just like we did before, I would like for us to factor an x out of the denominator. If we factor an x out of the denominator, what would we be left with inside those parentheses? 11 over x minus 11. Now, we can go ahead and drop those x's right there, and we have the limit as x approaches infinity of 1 plus 4 over x over 11 over x minus 11. Now, as x is getting really, really, really large, what's happening to this number? Going to 0. So wouldn't we end up with a 1 on the top? Because this number here is approaching 0. As x gets really, really, really large, what's happening to this number? It's approaching 0 as well, right? So what would we be left with on the bottom? And there's my answer. Does that make sense on how we're able to do that? You're okay so far? So look, y'all, right over here on this one, we're going to have a negative 111, right? Okay. Now, we have one last part to do here, y'all. This problem here. So notice, it's almost, yes, ma'am. I kind of have to work it out. Yeah, I kind of have to work it out, but I'm going to show you, Jennifer, on the next one. And hopefully, like, now we'll be able to like recognize patterns and all that kind of good stuff, okay? Yeah, so look, let's look at this one here, y'all. Now we're taking the limit as x approaches negative infinity of, it's still the square root of x squared plus 4x over, what was it, 11 minus 11x? Okay, so look, let's take a look here. Y'all, remember what we said up here at the top? The square root of x squared is equal to x as long as my x numbers are either 0 or positive. But the square root of x squared is actually equal to a negative x if the x numbers that I'm looking at are negative. If we're taking the limit as x approaches negative infinity, if I were to factor out an x squared from here, just like we did before, and we were to now say, well, what's the square root of x squared? But x, the numbers that I'm picking for x, excuse me, the numbers that I'm picking for x all are negative numbers. Wouldn't the square root of x squared actually be equal to a what? A negative x, right? Did I drop my square root earlier? Yes, I did. Sorry about this, y'all. Okay, well, I'll come back and look at it in a second, but we'll deal with that in 1 minute. I dropped the square root when I shouldn't have. I'll come back and fix that in a second. Okay, come back over here. We're going to factor an x out of the bottom over here to y'all. And this is going to give me, what, 11 over x minus 11? Is that? Okay, so first thing I'm going to do, these x's are going to cancel. So notice what we're still left with. We still have a negative, and then I have the square root of 1 plus 4 over x over 11 over x minus 11. Okay. Now remember what we're taking. We're taking the limit as x approaches negative infinity. So x are really large numbers, but in the negative direction. Okay. Whether x is really large numbers in the positive or negative direction, what happens to this piece? It approaches 0. So on the top, everybody agree I'm approaching the square root of -1, or the negative square root of 1, I'm sorry. And isn't the negative square root of 1 the same thing as -1? And as x is getting really large, but even again, in the negative direction, what's happening to 11 over x? That's still approaching 0. 0 minus 11 is a negative 11? So what's a -1 divided by a negative 11? 1 over 11, right? Because the negative over negative is positive. So right over here, y'all, I'm going to plug in positive 1 over 11. Y'all, I told y'all I had made a little boo-boo right here. What I forgot to continue with right here was the square root. It doesn't really change it because this guy still approaches 0. The square root of 1 is still what? It's still 1, right? Okay, but I did make that mistake. I should have kept the square root. I can't just drop the square root. I'm simplifying it here, but I still have it on that part. We were just lucky that it was 1 and not another number, right? Because it would have been like 4, or the square root of 4 would have been 2. You know what I mean? Okay. So, and there's our limits. So, question: you guys feel okay about how we're able to find the limits here? Remember, I think a couple of things to consider, y'all, is, I wrote it down here. Here we go. A couple of things to consider, I think, is this. And I'm going to do it like this, y'all. Whether x is approaching positive infinity or x is approaching negative infinity. If the top part of my function is approaching a constant, like whatever that constant could be, like 7 or -8 or whatever it happens to be, and the number on the bottom is large, whether it's large in the positive or the large in the negative direction, it really doesn't matter. Okay, so what I mean by large, like it could be a million on the bottom, or it could be a negative a million on the bottom. Does that make sense? So the bottom part gets really, really big, whether I'm looking at the positive direction or I'm looking at the negative direction. If the top number is a constant and the bottom number gets large, whether it's positive or negative, the whole thing is going to approach what number? 0, right? Okay. Then the other thing to consider is, let me scroll back up here. So we had it. Oh, did we pass it? Here we go. This is the other thing that I want to make sure that we understand. Is the degree of the top and the bottom. When the degrees of the numerator and the degree of the denominator are the same, it's always going to be that fraction of the leading coefficients. If the degree of the top, y'all, is smaller than the degree of the bottom, it's always going to be y equals 0. And if the degree of the top is bigger than the degree of the bottom, I'm not going to have a horizontal asymptote, but my limit is either going to approach infinity or it's going to approach negative infinity. Yes, sir.
Is this only true for limits? Sorry, is this only true for the limit for the positive side, or is it all of the limit for the negative?
Okay, so this should be for both positive and negative. Yeah, this should be true for both positive and negative. Yeah. So earlier when we were doing this, notice at this point, John, all we had been looking at was the degree is, I'm sorry, the limit is x is approaching infinity. So that's why when we did this one right here, we said, well, look, let's go ahead and figure it out because now we're looking at the limit as x approached negative infinity. We still ended up with 0. Okay. All right. So let's see. I think. Uh-huh. So y'all, what I'm going to go ahead and do real quick is I'm going to hit stop